Very nice feedback. Actually, I had to fly back last week from Bay Area. But yeah, first I want to apologize that this has to be kind of rescheduled. Last time there was like a technical difficulty, so we couldn't really get it going remotely. But I'm very glad that I can do this in person today. So today I'm going to talk about unlocking generalist robots with human data and foundation models. And so before I actually dive into generalist robots, I want to first focus on like other types of modern generalist systems. So for example, there's large language models, LLMs, and one of my favorite recent generalist LLM system is Cloud Code. And for people who have used it a lot, you know that if you set things up correctly, you might not even need to write any one line of code, right? And another one which like I don't have this personally, but a lot of my friends did, is Tesla full self-driving or autonomous driving. And like in the past couple of months when I my friends took me around on their Tesla, they never had to intervene at all. It was fully self-driving from one place to the other. So obviously there is a like recipe for generalist systems that works in other domains. So my question, and actually this is a question for you guys, is like why is there not a generalist robotics system? What makes robotics different? If anyone wants to venture a guess. Sorry?
Noisy real world data.
Noisy real world data is noisy, right? I think that's part of it, in my opinion. Anyone else wanna have a guess? Yeah. So basically, also real world, right? Real world interaction is what we
Just the cost of hardware.
Yeah. That's also another, right? I think there's all of these actually like tied, like we can all tie them together to one source, which is just, I think, data. Because, right, you need to collect data on your hardware, and your hardware is very expensive. So you can't, just spam like millions of robots in everyone's homes and collect data that way. And physical world interaction is very hard. So you actually have to sometimes go into the real world, right? And then to collect data there. It's very hard to simulate that or try to like, use some abstraction to get the physical interactions. So all of these tie back to, I think, data. And I think it is data that makes robotics very difficult to become general. And in this talk, I want to investigate, what are some potential solutions to that. Yeah. So yeah, as I mentioned, a common complaint in robotics is that there's just very little robotics data. So here are some examples of like robotics data we had in the recent recently in the field. There's things like RTX, and for example, that has like 1 million episodes, and like Pi recently published their papers on like generalist vision language action models, and they claim they use 10,000 hours of like what they call Pi cross embodiment dataset. But we know that compared to, I mean, this is already a very old like thoughts that I borrow from other places, but we know that compared to like the amount of data, like the avalanche of driving videos and like internet tests, like this is pretty much just a drop in the ocean. So, but I want to make the claim, maybe slightly you know different for like what most people think about robotics, is that robotics data is not just, maybe it's just not just robotics, robot images in and robot actions all kind of data. There's actually a lot of hidden treasure troves, which exist in the form of readily available data and models that can directly inform for robots, and we can leverage them to gain knowledge for robotics. And they don't probably exist as in the format of real hardware in people's homes, recording images and robot actions. So what are the hidden treasure troves of robotics today? What are the alternative, readily available sources of robotics knowledge? So one of them, and this has become quite popular recently, is ego-centric human video. So here are some like examples. I think these are just videos I took from some like startups that collect robotics ego-centric human video, and also like recent papers that also leverage this kind of data set. So you can see we can easily scale this up, right? Like for example, this one of them is like 100,000 hours. The other two are about like 25K hours. And also what are another source of like, potential knowledge that we can leverage for robotics is foundation models that's trained on also internet scale data, right? So we have things like segmentation, point tracking, even we can like recover the hand actions and hand pulls in the video. And finally, there's two-use agents. So this is something quite new, and I think not a lot of people perhaps have thought about using that as a potential knowledge source as for robotics. But in my later part of the talk, I want to try to argue that a lot of the robotics methods we use and modules that we use are actually can be exposed as tools that a coding agent or the two-use agents can use for the purpose of moving the robots around and make them very general and do useful things. Okay, so first I want to focus on the part ego-centric human data part, and in one of my earlier works, I investigated, is it possible to distill human videos into manipulation policies for robots? Right? And the paradigm kind of was like, we need to, learn some like general purpose, skill policies without a specific reference to a particular robot or scene or objects. Because if anyone has, trained behavior cloning policies, we know that we need to get a robot to a specific place and we need to like kind of like tell all the robot to do that thing in that scene with that particular robot, that object about 100 times, and then now we finally can have a policy, right? So is there another paradigm where perhaps we can start from like this kind of egocentric, and in particular in my work, the scope was like kitchen type of egocentric videos, and can we then like use that to train some policy that will work on the robot? And what is the recipe there? So the work I'm referring to is called ZeroMimic, distilling robotic manipulation skills from web videos. And basically on a high level, right, I try to answer the question without any robot data, right? How much information can we I try to be like, basically make a very controlled experiment, like without any robot data, just from human videos alone, how much kind of information or robotics things useful to robot actions can we extract from human videos? So I started from the human videos I saw and I just presented, like from the kitchen's data set. And the end product I want is something that can zero-shot deploy in diverse environments. So if people are familiar with living hall, town hall, skirt mesh, or whatever town, and some of the buildings there, you'll recognize that some of these kitchens, over there, are we just drive the robots there and see if we can do something useful. And at the end, we found out that we can, with the scope and time and resources I have, I was able to train 9 different manipulation skills, and I evaluated them in 34 different scenarios across various different object categories in 7 different kitchens in paid engineering. And the answer is kind of, yeah, there's definitely useful actions and manipulation skills, surprisingly, that you can get from no robot data at all. And the recipe is something like, I start from knowing what human hands are doing in 3D. So there's like a lot of 3D vision strategy here. For example, through various methods, recovering camera, recovering hand pulse, I can, here's a visualization, right, of like the hand actions, visualizing point cloud and project on images. So through vision techniques, I can recover the human hand actions, and they kind of make sense in the world around it. Even though they're slightly noisy, you can get like some like skipping hand poses in between frames. But nevertheless, right, like these techniques are back when I was using these kind of vision models, they're still not as relevant. And nowadays, there are definitely other methods to make that even more reliable. And after I know what the human hands are doing in 3D, I can train a policy to operate human hands. Right? So given an image of human hand and some goal that we want the policy to reach, and also like the pose of the human hand, I can then just use that data, right? Like I process the kitchen's video into this format, then I train a policy that will predict how the hand is gonna move. Right? So it will produce the trajectory much like, I'm not sure if it's visible, much like these trajectories you see on the images, right? Like one of them is for opening a cabinet or drawer actually, and the other one is for opening a cabinet. And you can see that, it produced something quite reasonable for these kind of actions. So it knows how to, and then these images are like images that's not in its training data. So it's able to, because it has seen so many like cabinet drawers and so on for a human data set, it's able to, given a new scenario, know what to do. Okay. So, and then the final step is deploying the human arm policies on robot arms. Well, there's one disclaimer or acknowledgement I want to make is that I think there is a fundamental gap between the robot embodiments and human embodiments. And so your kind of like usefulness and level of transfer will drop if the gap is larger and larger, right? So actually nowadays we know that if we kind of deploy this kind of policy, we train the policy and deploy them on a humanoid robot, where your cameras and your hands are naturally in similar kind of configurations as a human, there will probably be a lot better transfer, and you will need to use like less kind of like heuristic-based method for mapping. But anyways, I think still this doesn't like disprove the point of like having some sort of transfer, even though there's certain things that are really hard to learn from human videos. So one thing that's hard to learn from human videos is concepts and grasping. Because the robot arm I'm working with is one like robot arm, manipulation arm, and it has a different kind of grip rate than the human dexterous hand format. So I'll have to use some like human affordance-based heuristics to kind of map how I'm grasping from the knowledge I've learned from human videos. So for example, if the task is open drawer, I can use like affordances that I learned from human videos to tell me where the human would like to interact with the drawer. And that, again, is trained on the same like kitchen's data set. And given that, I can then generate a grasp of how the robot parallel gripper is going to grasp. But like critically, this kind of grasp generation model, they will produce hundreds of grasps, and it's very hard to identify which one to pick, right? But that's where the human affordance and human interaction human will come in and tell you, oh, among these like hundreds of grasps, actually like the one that's useful is which one that's closest to the human interaction and affordance. And then after picking that grasp, we can then execute a grasp, and that takes care of the context problem, learning context from human videos. And after you have made the contact with the object, you see from my previous results of operating human hands, that is basically the model is very good at like they're moving the hand in a way that will finish the task. So in this example, for example, I can give it an image of the robot current robot state, and also this goal image doesn't even need to come from like the robot in the scene. It could be even a human doing something, and it doesn't have to change for like different types of drawers. And also I'll give it the current like gripper pulse, and the pulse will just naturally be able to predict how the gripper is moving, just like how it's operating a human hand. It operates like a robot arm. So just want to quickly show some like more videos of like our various manipulation results in different kitchens, different setup, various fridge cupboard and so on. So here are some like skills that are like slide opening, slide closing, hinge opening, hinge closing. There's also I'm not sure what's. There's also things like pouring and stirring. Again, like these are kind of elementary stuff that can be learned from 2 minutes. Sorry, is there a question?
This is kind of strange, but to some extent, in a human built environment, everything is designed for human work.
Exactly.
So if you see a handle, you know that that's supposed to be opened by a human and not by an octopus.
So yeah.
So I'm wondering, are you essentially trying to back chain from that. In other words, you can just infer that any sort of
Exactly. Yeah.
thing is there for a purpose.
That's a great point, right? Because like you said, a lot of the tools and stuff, and then we have knowledge of that somewhere on the internet. On YouTube, we have people cooking like recipes of like cooking food. So we don't need to specifically know, oh, there's a knife and I have to grasp it. Like that knowledge doesn't have to come from only robotics data, which is quite expensive and hard to scale. And like, okay, this is where I have to interact to open the drawer. Like that kind of knowledge, I personally think can be derived from even from like noisy human data, which is very scalable and already contains this level of information. Maybe the low level, like, how do we specifically like do the context stuff like I did like in my current in my work, can be learned from a little bit of robot data. Like one of the model for grasping is a model that's trained on like various parallel gripper robot data. So the one in the middle. But yeah, I agree with you. Like the rest is common sense knowledge that people know, and therefore like human videos will already have that information. Yes.
I have a question. When you use the internet videos, is that to train the policy? Then the question might be the human in the video might have like information different from the video itself. I mean, like for example, the history of the environment, or like if we have like things that larger than the captured camera. So
Yeah.
how do you overcome that?
Yeah. I think this is a very good question, actually. I think back then, I think people are just using any sort of like human videos, and I think there's definitely still stuff that you can learn from that type of like very in the wild human videos. But now people have realized that like human has more context than what the hardware is able to. For example, maybe like I can do like because my peripheral view sees something there, I can even do something here, do something there. I'm not even looking at it, and then I can do some tasks there, right? So that's one example of that. So actually, I think nowadays when people collect ego-centric data, just like I showed in the startups that collect 100K hours, they have started to realize, okay, like what is the type of data that can be useful and that's high quality for robotics. And even in the wild data that we see on the internet, yes, there are cases where there's low quality, but if we can get this kind of first principle understanding of what makes a data set high quality, we can do a lot of filtering and then to like extract the high quality part from the internet. And actually, even in this work, I had to do a lot of filtering because I think from the lessons of training large models, right? Like data quality definitely matters in a sense. Like for example, if my vision model hand model predicts 2 right hand in the same view, right? I shouldn't be using that data. Any other questions? Yeah, I was just talking about like various skills. Yeah, so just gonna quickly go through some like skills that we are able to learn. These are just very like rudimentary kind of like skills that that's very like subtask like, right? Hopefully in the future, at the end of my talk, if I have time to get to it, I will show something that's like much more complex in terms of being useful in the kitchen as a preview. But yeah, this is like one initial like investigation that was cutting. Yeah, and then the idea is that because human data is a very valuable treasure trove for robotics, we can have a growing library of basic skills. And nowadays, perhaps this is what we can call a vision language action models, where your skills are conditioned by language. And these are able to be reused in different scenes and different objects and viewpoints. Yeah, and also critically, right, like it's because it's learned from human videos, though there is some heuristics we have to do to map it to robot, but that also means that I'm not like constrained on one robot. There's I can kind of move. I'm able to move like another type of robot like this to video example, and I'm even able to move robots in simulation, and it has never seen data on that robot before. Whereas the robotics policy often require data that's classed on that exact same embodiment or in that exact same scenario. Yeah, and Oh, okay. Even though robotics manipulation is evaluations is very hard, we try our best to kind of like deploy these in different scenarios we see and get some quantitative results. And I think the high level, message is that personally, when I saw this policy with having seen no robotics data, being able to do these tasks, I was just so happy and excited, and I was genuinely surprised that it's capable of doing something, even though these are simple coarse stuff. It's not like like inserting a USB or something very cool or like a fine grain. But I'm still generally like surprised that we can have some zero shot policies learn from only human videos alone.
Like, just quick question.
Sure.
It's interesting that picking has a low success rate when I feel like a lot of manipulation has been focused on picking.
Yeah, that is true. I think that is actually a very good question. The reason is that again, there's an embodiment difference between like how you're in your view, like humans pick up stuff, and humans always like try to pick up stuff that's like extend your arm, like grab it like this. And so if you don't like deploy the policy carefully, so in this kind of deployment, we often have to like structure the camera and the arm in a very similar configuration as how the human configurations. And as I mentioned, right, like the proper way of doing this is probably train a more expressive policy and deploy it on an actual humanoid with dexterous hands. But because of that limitation, it often struggles with like just the copying some human, so it's not grasping the way a robot would like lift it out. For example, you would just like try to retract it and and pull it back to like a fake human body, if you will. Yeah, sometimes maybe not have free. Oh yeah.
So going back, sorry, how about citing? So all these various visual action model classifications.
Yeah.
You essentially have a classifier, a video classifier that will put them in one of these groups and kind of come up with
Oh yeah, that's a good one.
instructions from that.
Yeah. So we could, and I believe right now a lot of like human videos data set are being labeled that way. But at the time we were using the application data set, they actually have sparse annotation. So it already came with annotation of like these clips, this clip. So the way the data is collected is actually people just wearing GoPro in their home and then just make dinner or make breakfast, and then after that, some like annotator will come in and say, oh, this from this second, that is cutting a tomato. That second to that second, that's opening a fridge and so on. And I'm able to just from that, like annotation to get basically all the videos of cutting, for example, or all the videos of opening fridge. But I think what you said is also very valuable to.
So once you trained it on the ratings data,
Yep.
you feel that you could kind of maneuver it over to unlabeled data, unlabeled video segments, so they could kind of generalize hierarchy of what slide closing is.
As I showed like before from the images that it has never seen in its data set, but he's able to like have general, if that's what we're asking, he's able to have general generally correct trajectories of like opening fridge and so. Is that what you're asking? Like, does it transfer to unseen videos?
Right. So in other words, you don't have to categorize the one.
Yeah, I think we still need to kind of like condition the task in some way, but this is actually I think another good question, because if you condition on, for example, the goal image, right, then you don't need to do any categorization. You just need to basically take any frame in the middle of your entire video and say, this is my goal image, and take like the actions before that and say, that is my action, right? In that case, you don't need to categorize. So if you want a model that's able to respond to language, for example, then by default, you have to kind of train on language data, and some level of language annotation might be needed there, whether it's like autonomous using a video model or by hand using like command address. Cool. All right, I'm gonna quickly move on to, so the paradigm we solve here is that, to avoid the bottleneck of like images in actions are kind of robot data, we're using like various modules, and that's trained on other data items, not just from robotics, right? So there's the grasping model that's like trained on lots of robot grasping data. There's the structure from motion data that's like, trying to tell where the camera is. There's human videos. there's the hammer, which is like a hand pose prediction model that's trained on human hand videos and so. And all of that like kind of all these modules kind of enables a more general system like ZeroMimic. And this is kind of in contrast with the Pi data set we saw, which is throw out images in an action result. I'm not saying those data are not used for inferring any sense. They're actually very high quality. I just think potentially, this is a way that we can scale up beyond those like high quality robot data. And so like one like basically insight we can get is that foundation models as modules are very valuable sources of robotics knowledge. And this, like segues well to the next section of our talk, which, discusses how foundation models, potentially trained on internet data, can also be useful for robotics knowledge, not just to extract actions and understanding from human leaders, but by themselves, right? They have a sense of understanding of the objects, understanding of motion, and so on. So can we use this kind of like understanding and knowledge to better enable generalist robots? So here I want to focus on this work called Constrained Object-centric representation for robotics composed from what and where foundation models. This is actually from a long time ago, where the segmentation editing model just came out. If you guys recognize like the segmentations there. And the key idea is basically, can we like compose kind of like these foundation models trained on internet data that understands, for example, understand the what in the image. Many type of model can do that, right? For example, like resonant and so, and also understands like the where in the image, like specifically here, like some kind of like image 2D segmentation models, and we can combine them to produce like very useful representations for robotics. And again, here the intuition is that we don't necessarily need to learn where an object is, what it looks like, and so on, like only from robotics data, right? That will be very expensive, but that knowledge has already been distilled into kind of a vision foundation model by training on internet still data. So sorry, what are the key components in this methods? First, given a scene of like multiple objects, we first find out where are the relevant objects and what are their contents, right? So where would be like, like we need to segment all of these and understand where they are, and then given like one object, what is the actual object? Is it apple or orange? And finally, how should the robot act to perform tasks given these what and where object-centric representations? So first, like this part is more like relevant to where are the relevant objects. So basically, after segmenting like the scene, we can get a lot of masks, right? But the issue again, and nowadays there's probably better ways of doing this using language-based segmentation. But at the time of this work, we use like various algorithms such as non-mass suppression and Hungarian matching with like semantic features to then first of all figure out like, okay, like these are like, sometimes it will give you like overlapping or redundant masks, but to figure out what are the final set of masks that are like corresponding to each object. And then because we have a slot, like a object slots, right? So we can bind these objects to their corresponding slots so that every time I get an image with the apple in it, and I can detect the apple will always go to some slot that's corresponding to the apple. And in terms of what are their items, we found out that surprisingly, even if you give a foundation model that's trained on like actual images that's not maxed out, we just give it the max RGB of each object spot, and they're able to have very good visual representations of like these masked RGB images. So we literally just give them like what you saw here, right? Just an image with only the object and everything else masked. And finally, for learning level actions, we again just use something that's like behavior cloning that's very convenient. But importantly here, we apply like a self-attention layer at the end so that this permutation invariant doesn't fixate on the order of the objects. And also we found out that like through this more like maybe leveraging internet knowledge about where objects are, what object is, we can learn like much more efficiently and perform much better and be very robust. So we tried perform a bunch of experiments, like various tests in the simulation. Oh, sorry. And in the real world, and yeah, a summary of like how it performs, right? So basically, in terms of like behavioral cloning success rate, compared to previous like end-to-end kind of embeddings and previous like object-centric methods, we are able to like perform much better. And I'm going to like try to get a intuition on why. And these are just some videos of like the policy acting in the real world compared to the red and green bars, which are like more like not object-centric representations that doesn't leverage this kind of like vision knowledge from the internet. And we found out that really like what actually makes like poker our method very general and robust and performant is that it's able to enable like systematic generalization to test time variations. And there's often a lot of test time variations. For example, your object might be slightly at a different place, and these are like more like critical type of test time variations where you introduce a new object in the scene, or you introduce a new background, or and so on. And in these specific settings, we see that because end-to-end method is often like overfit to one type of scene, so the performance would drop like significantly, sometimes even to zero. Whereas because like we kind of like inject this kind of semantic knowledge from vision models into the policy, then it's virtually unaffected, even if you have disturbance and test on variations in the scene. Cool. Yeah, so that was one way of using foundation models. There's actually a lot of other ways that my ongoing work kind of like also tries to leverage vision foundation models for different purposes, but for the purpose of time, I think I'm gonna skip that, and we can talk about it like after the talk. But still, I do see that there's actually certain types of limitations of these kind of modular systems where you have very predefined program over modules. Like one example in the ZeroMimic work that learns from egocentric videos is that you will first have like a graph affordance, and then you generate graphs, you have motion planning, and then you have a post-graph policy, right? So this actually limits the expressivity of the policy. What if that is not the way to perform a task? What if the task requires not grasping first, right? And because of these like kind of leaky abstractions, it's kind of brittle and sometimes hard to recover because you have a predefined recipe for using something. Then if that recipe fails, then that bottlenecks the success of our entire system, right? So after those works, right, I try to investigate, is there a way to build more scalable and robust general system that use these modules, right? So my insights is basically like, over the past like many years, there have been so many tried and tested, battle-proof, like modules and methods, maybe in a more traditional sense, right? There's control, motion planning, vision stuff that are working very well in their individual domains. But it is a lot of like basically labor-intensive engineering to try to combine them and make them very robust in a specific scenario. Right. So we see that in like factories and so on, like where they are like deploying robots, not using like the current like end-to-end policies. They often have this kind of automation procedure where they first try to identify where the object is, and then like try to produce a very robust control, and then and so on. And that usually takes a lot of engineering. And nowadays we have like vision language action models that can be very good at like using different tools. So in a way, right, maybe graph affordance is a tool, and even neural network policies, vision language action models, they're also a tool. And maybe a 3D foundation model segmentation, point track, all of these are just tools that can be exposed to an agent, much like how when we were using cloud code or any coding agents. There are various like model context protocols, MCPs, like going on the internet, download this image and so on, that the coding agent can use to enable us to write better programs and have basically more general and capable systems. we can also view robotics potentially in the same way, right? So now I'm gonna transition to talking about how do you view robotics as like a tool use scenario, and therefore how can we use tool use agents to enable general robots, and in a sense like we can get a generalist modular system if you use them correctly. So the word I'm going to focus on is called Maestro, orchestrating robotics modules with vision language models for zero-shot generalist robots. So basically, on a high level, Maestro works like this. So it starts from kind of like, it starts from like a large toolbox, and it's pretty important to curate a very high quality set of tools. And then the coding agent or the tool use agent will then decide given my current scene, what are the relevant tools that I can use to execute my task. And then you will decide, like maybe I need to generate a plan for the next bit of the task. Like, for example, if I'm cutting the banana, I need to move the knife above the banana, right? And then you execute that, and then give based on the execution results. You will then again see the execution results in images and send it out, printing and logging principles, whatever. And also having access to the previous prompts and history of execution, and tools, you will then decide, did I succeed? If I succeed, I need to plan the next bit of task. If I didn't, then I have to replan to finish the current bit. So this is based on like two key insights that I've had. The first is that VLMs can use tools, right? Tool use agents are very good at using tools. So let's just give them let's scale up the number of high quality tools we have. And this is from a basic understanding that a lot of robotics module, even like things that are useful to robotics, are actually usually expressed in code or can be interfaced using code. And that's why I have like this part and of many tools that we can call, ranging from like perception and geometry to control methods, collision avoidance, to even like VRA policies, pi 0.5 as well, or image editing. Right? And the second insight I have is that they're very good at reasoning, so we should let them reason in closed loop. And this is because there's some previous exploration of like this code as policy type of strategy for robotics, but they often just let the policy run in open loop. They will generate a script, and that's it. They will just run the script. But we know that that's not how it works, right? Like in physical real world interactions, you always have noise. You always make mistakes. You always, objects might like, you run into some objects, it might change the state and so on. So you need to be able to respond in closed loop, like what actually happened in the scene based on the policy. So because they're good at reasoning, we can let them reason in closed loop. So we will first, generate plan, a little bit of plan, execute them, and then look at it again, see if that works, and then plan the next subtask or maybe replan. So here's like a just a simple illustration of how this works. Notice that I have a cursor clicking the different like methods, but that's actually just a visualization. Like in reality, I'm not choosing what it should be using. The tool use agent just naturally choose, by itself, kind of like decides what kind of like modules or tool you will be able to use. And at the end, I will show like some analysis that shows like it's actually they sometimes even choose like various different tasks, depending on what the task is doing. And then by just like I have just this one like a kind of interface and coding agent that has all of these tools, and I'm able to just use the same stack and system and give it any kind of task, even not on this robot, on like other robots, and it's supposed to do something usually quite reasonable. And based on our access to the open source VRA models, it's definitely like much better than performs much better than the open source VRA models that we have access to. So I can zoom in a little bit on the tabletop results, because there's also a mobile manipulation results. In terms of tabletop, right? So I'm comparing to the previous like state-of-the-art work that uses this kind of like code as policy strategy that's like presented in Gemini Robotics technical reporting last year. and also compared to two like state-of-the-art VLA policies, the vision language action models. One of them is Pi0 and one of them is Pi0.5. And the way I like evaluate this is I try to be very systematic and like general in my evaluation as much as possible. So you can see these are some examples of my evaluation. Like every trial is different. I will try to give it a new objects. I will disturb the visual axis or like changing the object, the position, even the language I give it to the system. Right. So this is following like a recently proposed way of evaluating like generalist robotics policy called Stargen, and you guys can look at that work for more details. But basically, after all of these very general evaluations, we found out that basically the finding is that the previous coalesced policy systems, because they also kind of have this semantic planning ability, it's able to usually say the right things. Oh, right now I need to do this and probably need to use that. But because it doesn't have like the closed loop planning system, and also it doesn't have the access to the level of high quality tools, because usually the previous work considered tools a very very narrow sense, like detect object and move gripper, that's it. Right. So it's not able to translate the high level thoughts and reasoning into low level robotics actions. And also on the other hand, the like Pi0 and Pi0.5 like vision action language models, they're very good when they see something that's like, for example, like one of them is like probably like hang cup or picking. Like we know that those things are like in the training data of what's used to fine tune Pi0, Pi0.5. So in those scenarios, and you can see it here as well, like in the markings, right? Like for example, the blue marking corresponds to each marking basically corresponds to a different methods of performance, and it's from 0 to 100 from left to right. So in many cases, in the top left corner, all the methods are 100%, right? Because that is picking up a ball like that is very in distribution with what like the vision language action models have seen. But as soon as you change the language or change the position slightly, change the background object, that we know is kind of like out of this distribution for the VLAs, then like definitely struggles. And I know, okay, yeah, as we collect more robotics data, yes, we'll finally be general. But I think there's two arguments I want to make, which is like I think there's still like very value in terms of there's always like all of these distribution scenarios until you cover the entire world. And what do you do in those scenarios? And also later in the talk I will say that maybe this is another way to collect data that doesn't use human labor in those all of these distribution scenarios for robotics. Okay, so so here are some videos for the like tabletop results. So I try to give it like various challenging axes of current like manipulation policies. For example, pick and place, rotation, kind of like you have to reason about geometry, reason about like deformable objects like folding, and reason about like articulated objects. On the bottom right, there's like opening cabinet door, and also like some even harder tasks. Like for example, on the top right, we have like kind of a memory task where you have to erase the instruction for doing a certain task, and then the robot has to follow that instruction and then like stack the blocks using the instruction. So there's like a lot of memory involved. And here as well, right? Like clean the table, largest object first. It has to reason about it has to first like understand, oh, these are the objects in the scene, and these are the largest ones, these are the smallest one, and then this is the order, and that's how I need to clean up the objects. And so like there's also other things where you have to reason about like using tools or reason about like the geometries of a like mud stand, for example. So there's definitely a lot of like reasoning and planning here, and I think being able to use different tools in a closed loop fashion definitely helps these very challenging scenarios. Otherwise, for like end-to-end policies. So another good thing about this kind of method is that I just need very minimal change in like how I control the robot in the low level, which is anyways like just giving it as an API usually. And now I can just move the system on a new robot without collecting new data. Right. So for example, by the way, this is also I think this is AGH, various different places in AGH. I can just deploy this system on a mobile manipulator. And for example, let's focus on this one, right? Search and bring back Apple. Like this policy has to start from all the way like in the back of the room, where the apple is here, and it is all the way over there in the other side of the room, and it has no vision of where the apple is. So this definitely requires a lot of like long horizon planning, memory, and understanding where I am in the room and so on. But it's able to like go around, try to look for it, and walk towards the apple, and I finally see there's an apple, and let me bring it back to where it is. So yeah, I mean, I'm sure like if you collect a bunch of data here, yeah, this robot can do it. But I think for me, it's very satisfying to see that the robot is able to do that without any data collection. Actually, today is kind of difficult, but in my previous like group meetings with the Nash, we will actually just like grab the robot in the room and say, hey, like, what do you want the robot to do? And have some objects on the table, and it's supposed to just like zero shot be able to do that, which is pretty cool. And sometimes when even you make some mistake, it's supposed to like reason about, oh, this is a mistake I had, so let me try again with a different plan. Yeah,
What's the
another yeah.
this agentic system versus the traditional damping system?
I mean, in traditional time-based system, you still have to manually describe, oh, this is how I use tools. This is a library of like concepts I have. This is a tree and graph of like how these concepts relate to each other and so on. Here, this is like much more like flexible endpoint, right? And the traditional time system is a lot like the prior work I did, where there's a lot of predefined flows and procedures, like how like ZeroMimic and so on was set up to do. And this is exactly trying to do the opposite of that, where I think there's a lot of limitations if you have one template to do something or one set of ways to do something, right? So in a general sense, right, to be able to act very generally and even to automatically collect data, you need to be able to be flexible and adaptable. And in those cases, I feel like the predefined, I think TAMP still has a lot of like value in many other constraint scenarios, high performance with guarantees and so on. But in a more like general purpose robotics kind of sense, I feel like losing some of these heuristics and heuristics and inductive bias actually will help you to be more robust and scalable. Okay, yeah. So another cool downstream, there's many downstream applications of this, but due to time, let me just talk about one of those, which is you can use it to autonomously collect data. So because this is like a zero shot, kind of like you don't even need robot data to do a task, right? But as you can see from previous, like examples, the way it does it is not the most smooth and high quality way. It sometimes takes a long time. You need to pause at certain places to think, and then like do something again, right? So, but in real world robotics, we want something that's very smooth. We want like fast acting like policies that can do things very accurately and fast. So, and also there's sometimes a lot of mistakes. Oh, I try to use this tool and didn't work, and I have to recover. But given all of that, we can still use that to use all of that as like someone recently said that whenever your robot is doing something, you shouldn't throw that away, right? To contribute to the growth of physical intelligence, we should just keep all our like physical data. And this is precisely what that's doing, right? Like I think we always say, oh, like once we have the coverage of robotics now to the entire world, then we solve robotics. But yes, like the question is how do we reach there? And I think, because we have so many like very good modules that can be very robust in different scenarios, maybe one way of reaching there is try to like recycle this good old-fashioned engineering that we have already done, all the previous traditional methods that are very good in very narrow scenarios, and try to combine them and make it into a modular generalist. And as a modular generalist, even though the trajectory is not the smoothest, you can then just keep running it, and you can you can clean up the trajectories post hoc, and then use that as a training data for your like end-to-end policies. And that is one of my vision for how you can generate synthetic data for robotics.
So when you say synthetic, you're basically actually going to run the robot, just give it like 100 randomly generated task sequences or plans. Is that?
I mean, so for example, I want this robot to close Chris's laptop, but my VLA models has never seen Chris or his laptop or this room and so on. And maybe it has, where then it will give you a very good performance, but if it hasn't and it's out of distribution, you wouldn't do anything reasonable. Whereas this kind of model, because it's able to identify, oh, this is a person, this is a laptop, I'm in a room, this is kind of the geometry and for clothing, this is a control method that I can, or motion planning method that I can use to avoid a collision, even has some guarantees and so on. So I can like leverage all these tools to do something that's reasonable, even though it might be slow. It might make some mistakes in the tool calling sequence. Right. So that data, I think, can contribute to our like growing body of like covering the entire world. And maybe that's one way of doing that.
But that actually would be an interesting test because we identify the person and you identify the laptop and close.
Well, yeah, I think it depends on how you specify the task for sure. Yeah. Yeah. So finally, I just some further analysis on like Maestro programs, right? So there's a lot of things, but basically the high level insight is that it's able to generate like for different tasks and so on. It's able to generate very diverse programs. So here are like various different tools it has, and like kind of like the graph for it, like sequence of how it goes from one tool to the other. And here's like some insights on like, like what are the different tools and their like frequencies and so on. Obviously, like Move Gripper is definitely the highest used tool. But the point is that like it's in this case, it's never like a predefined procedure anymore. Like now you can actually have flexibility, but you preserve like all the niceties of and then the robustness of the modules that people like works really hard to design, and it's very useful in many scenarios. Okay. Yeah, as I mentioned, right, there's the limitation is, for example, speed and maybe dexterities. It's very hard, for example, to describe crunching a paper towel, just in language, right? Because there's so many, or like, like crunch up a shirt or like folding something. Like it's, some of these things are really hard to abstract using words. But I think that is okay because for the low level stuff, I think like end-to-end methods, they're probably better at like approximating the complexity there. And they're getting better, but it doesn't mean that we need to learn every single thing from end-to-end data, right? Like there's a scenario where, for example, if the company's employee has to respond to like some like lights at the end of the tunnel that says, "Oh, you have to start working, stop working." Do you even learn all of that from only like robot data? Hours of observing like their lights that turns on like every hour. I feel like that doesn't make any sense, right? So basically, there's still things that you shouldn't only be learning from end-to-end, in my opinion. And the dexterity, maybe you can, if that is really a challenge, it might not even be a challenge in many tasks, but we can leave it to the end-to-end policies. And another thing is that everything I talked about in this work, the coding agents, the tool use agent, VLAs, all the tool modules, they improve every month. There's something new that's much better. Like since I worked on this, like there's like new VLAs, new like pointing methods, new coding agents, new segmentation models. And right now there's actually some 3D, which I haven't even. And my point is, if all of these things are like just scaling up and getting better and better, then for free, this method will just like improve by itself without even doing that much work. Yeah. Okay. So finally, I want to end the stuff by just having a touch of like basically my understanding of like the generalist systems. So I talked about a lot about how to leverage, various different sources of knowledge. But in the end, I think, another way of looking at this is that we have some kind of a recipe that works for general system, and it kind of looks like, pre-training from diverse data, mid-training from synthetic data, and post-training from in-domain data. And there's a lot of analogy of that in terms of large language models and self-driving. And here I just picked a large language model where you go from very large scale, large diversity, but probably low quality data, and to the low scale, low diversity, but like high quality data. So imagine cloud code, right? So yeah, it has a lot of high quality coding data for sure, but it also is trained on internet so that it doesn't need to learn a basic like arithmetics or like translation or basic English grammar for only coding. And that will be quite expensive for cloud code. And I think there is also a analogy for robotics in some sense. So I talked about like some of my previous work, but like for example, right, like ZeroMimic, the one that learns from ego-centric human videos, could be like the potential pre-training source for generalist robot systems. Maybe like as I talked about, like the Maestro that use synthetically generate real robot data using agentic tool strategy can be the mid-training synthetic data. But I think it is still important to know that like maybe we still need some level of post-training data that's high quality, and that is kind of pretty much what I was working on at Skilled during my internship. Given that we have like very good pre-training and so on, like we can start from the brain. How do we get to a very, very performant robot process that does very, very hard task? And one of the tasks that I try to do is this like egg cooking scrambled eggs end-to-end, policy that's very, very long horizon, and there's many, many different subtasks, and you have to basically many difficulties for the current robot learning system, such as grabbing the egg will be a very precise action. Like if you grab it just like a little bit too much, then it crashes and explodes. If you like didn't close enough, then it drops, and the eggs will move around as well, and then you have to kind of like decide when to. That was me eating the tasting the egg. You have to decide when to stop stirring and stop stirring the pan, stop whisking the egg and so on. So this is like a very super long horizon and very difficult tasking. And then I think the part that I like it the most is that it actually produces something that's quite enjoyable and of value. Now I can actually, for example, during like this year's spring Lunar New Year, right? My friends wanted to make child eggs dumplings, right? And then they didn't have enough scrambled eggs as like the ingredients, so I can just like ask my robots, hey, like you have an hour, and just like cook many eggs, and I take them to the Lunar New Year party, and they have the ingredients. So it's actually very useful. So that I'm very happy about producing something that's like can be used and of value to people. And but we know that just doing it once doesn't actually count, right, in robotics. So the bigger question is, can we make a super robot and do it repeatedly? Because when you deploy this kind of thing in a kitchen or in any real world scenarios, you don't want it to make a lot of mistakes and mess up the things. So you want to be robust and be able to do it over and over again. And this is a video I took from like a few weeks ago, where it can do like this task like 30 minutes without interventions, keep doing it. But I think we've have a strategy where you can keep growing and growing to hours and so on, like without making any mistakes or intervention. And yeah, at this point, like this is already even much more robust than this. But yeah, so the hope is that like this research that I did doesn't take away from all the previous stuff I said, that learning robotics from alternate source of knowledge, but more like, okay, once we have that brain, once we build that, how do we convert that into something that's like performance with like limited resources in terms of robot data and so on, and also robust, and we can deploy them in useful scenarios.
So it learns the whisking time and how to break an egg and all that from video generalization from videos. So
There's definitely part of like knowledge that it learns, not just from robot data. Right. I think, as we said, right, like for example, like learning to localize an egg. Because the eggs, they look the same, but if you actually need to grab them, they're actually very like not a single egg is the same. And also, just you can take a look at how the cracking is happening here. We actually introduce like just like how humans crack eggs, we need to drop it, and it like produces a crack, and then we pick it up, and then the other hand has to look at where the crack is and pull the egg open. Every time you drop it, like it's a different type of crack, right? So basically, my point is learning all of this from pure robotics data doesn't make a lot of sense to me. Yeah, but there's also definitely things about like low level stuff, like how do I touch an egg, what actually constitutes like pulling and so on, that can be learn from useful like high quality robotics data. But yeah, I think it's a combination of both. Cool. Yeah. Anyways, so the key takeaway of my talk is that if there's one thing is that robot data is very useful, definitely. But not all robotics knowledge must come from this type of robot imaging, robot action style data. In the future, where we have generalist, general purpose robots. Oh, oops. Yeah, that's the end of my talk. Thank you.
Like no question.
Okay. Yeah. I mean, you should.
I just let me to understand the tool. So, in Maestro, basically you're using like this higher level BLA, so orchestration layer, right? So it chooses cool.
Yep. Yeah, much like how cloud code chooses different MCPs.
Now these particular tools, do you provide them like these dozens of tools in other beforehand?
Very good question. So in this product, I do, because in the beginning I didn't want to, but I think I realized that like just like in cloud, you sometimes have to specify like, oh, these are like the high quality tools that are relevant to my task. These are the MCPs that I want to choose. I found out that if you introduce like a bunch of low quality tools, then you will just sometimes be in vicious like cycles of correcting the mistake but not being able to use the right tool. So I did have a lot of tools that I curated, but I handpicked them that I know that are like reliable and high quality. Yeah, so quality is very important. However, I think there's another PhD student in Grass called Yifei, and he recently had a tidy ball, like autonomous tidy ball project, which on some level is kind of related, where he uses OpenClaw, if you guys know what that is. Basically, he doesn't have to my understanding, he doesn't have a like pre-specified list of tools, and the agent can just go on the internet, read what people say, and choose the best tool corresponding to that. I think start a tool. If anyone has used OpenClaw, you know how like it's kind of like a self agents that can do a lot of things. So there's a chance for that, but I think you trade off some like at the execution time. If you have lower quality tools in your tool set, then you make more mistake and you think longer and so on.
Yeah. So like for example, the tool of moving or to this is
Is the tool like standard IK or is it
a VLA that produces a different reason.
Like I don't know. Like you can choose either. Yeah. No, it has access to. Sometimes it's like let's see. Sometimes it's just a moving by using IK. If it can compute, if you can use like the 3D information it's seen to compute. Oh, this is the like pose for like right above the banana. Actually, I think I have a better example of this if we just look at this video that my collaborator made last night. That's on my website. That's on the project website. So basically, I go forward. It kind of like has like different perception of like these are where the objects are, and in sometimes they have like object positions expressed in 3D and so on. And obviously like I think in this example that there's no like using VLA, but you can basically imagine, right? Like using VLA is pretty much like that as well. So
Yeah.
if it decides to call the VLA using some like language command, like stack the orange block and green block, you can do that as well.
If you've run this a few times, can you optimize the speed because you're something?
Yeah. That is a very good question. Yes, because I think you will have you don't make mistakes, right? Like if you have a better understanding of like, oh, these things didn't work. Actually, I have some results where I can run multiple trials, and over time, if it has context of how the execution went in the past, then you are like improve. And so there was an example where it was only opening the cabinet 30%, but like over 4 different trials, they opened 100% by looking at the previous results that I didn't include because, yeah, but I think that's a good point, and then it's something that I'm thinking about for the next stage of this project.
I mean, actually, like the best case for this is like one shot the code and then next.
Yeah, I think once you're more and more sure about what to do, then you need to be less. You can be less and less closed loop, and like hesitant about, oh, let me generate only a little bit of code and then execute it. You can generate like a lot of code. But in the beginning, no. Sorry, is that a question?
Along with like something like the test, like, collect all the vegetables, chop them, and put them in a bowl. Then have a bunch of objects, some of which are vegetables, some of which are not. Tools that are appropriate for chopping, like a knife, and maybe other things like a wrench that isn't. And a bunch of objects, some of which could be used as a bowl and others that couldn't. And then would it basically get up to identify all the objects in the scene, and then it would figure out which ones are superfluous and which ones it should do.
I mean, I think basically it inherits all the semantic understanding of like a GPT or like
That although a lot of that work is just done by the
yeah, because the coding agents, the like ChatGPT and so on, they understand like if you upload an image of what are you describing and ask what are the vegetables that are like related to my task, you will be able to just like you see a lot of identifying the right objects insane. I think it's able to do that very well.
Saying like there's vegetables here.
Yeah, for sure. Yeah. It's able to like reason, right? Like our vegetable is here and so on. Like you see here from the planning visualization. I'm not saying that end-to-end policy cannot. I think there are ways to embed that as well. It's just that it's very hungry for data and hard to cover scenarios as part of distribution. Yeah. Like for example, in my own end-to-end policy, there was like quite a long horizon scenario with a lot of objects. But I think like to be able to scalably do like, oh, I can do this for the scrambled eggs, but like 100 other recipes as well. Only using robot data is not the best, way to scale this up.
Thanks, Junyao.